Okay, let's get this show on the road. So, one of the questions we had in the community was around this idea of finding the number of solutions between inverse functions. So, I believe this one specifically came from Jacaranda, and we were told that we had some square root graph. It had a plus c in there that was attached to the inside of the square root. And we're told some other specifics about, we have maximal domain, c is a real number, that sort of thing, just to give you a bit of background as to what the potential values could be. And the question, or questions, are based around where the intersection points will have either no solutions or one solution, exactly, one solution. This is actually a kind of common question that comes up as a bit of a challenge. So what I've got here as an example is in fact one from the 2023 exam 2. Something very similar happened where you have some function, h of x, which isn't shown here, but it is just some other function, and you're told the inverse of that function is equal to this, and we're told find k such that we have an intersection point. So it's a common thing that comes up not just in the book, but also in an exam situation as well. So the key with these kinds of questions is to realize that the inverse can only ever intersect with its original function along the line y equals x. That's because it's a reflection in a line y equals x. And so it's going to end up having to only intersect along that line. So you see here an example, if you had c equals 2, so if you were to sub in c equals 2 into this function, you would have f of x, the green line, and you can see that its inverse is that reflection in the line y equals x, and you can see that it's been that it intersects at 2 points. It intersects here and it intersects here, but both of those points are along that line y equals x. Okay, so under that circumstance we had two solutions. If you want no solutions, it just means that what you want to do is shift this green function, the original f of x, to be to the right of the line y equals x, or underneath the line y equals x, more specifically. Because you can imagine if you're shifting this one slowly right, this blue one will have to go left, until it eventually no longer touches. And you can see that under this circumstance. If you sub in c equals -2, so if you put in a -2 onto your horizontal translation, you are shifting it right. If you put in a c equals -2, you get a graph that looks like this. Right, you can see f of x is now entirely below that line y equals x, and therefore its inverse is going to be entirely above the line y equals x. Just real quick, when it comes to finding inverses, that's usually not the challenge. All you have to do there is swap the x and y and then rearrange to get y back on its own. We can do that quite quickly. So if I were to just do it purely in terms of c without any of our substitutions, it would be you have f of x is equal to square root 2x plus c minus 1. We'll call that y, so this will be an x in here, 2y plus c, take 1, and then all you're doing is getting that y back on its own. So you're adding 1 to both sides, because the square root of 2y plus c, squaring both sides, x plus 1 all squared is equal to 2y plus 1, subtracting 1 and then dividing by 2. X plus 1 all squared, subtracting 1 and dividing by 2 equals y, and therefore your inverse function is that. Where did the c go? Right, I miswrote the c as a 1. So you're subtracting c, in fact. And so that'll be your inverse function purely in terms of c. That's why you see all of these inverses here look pretty much like that, but just with different values substituted. But okay, so for our actual goal, we want to find no real solutions, which means they don't intersect. Well, here's one of those cases. If you have c equals -2, they will not touch. Fair enough. But that's only one possible answer, right? We know there's going to be a range of possible answers. We could have c equals -3, shifting it even further to the right. So really what we want to try and do is figure out where does it barely start touching. So what is the last point at which it touches, from which afterwards it will never touch again? That's what you have to find if you want to find all the possible c values. In other words, the only way that can happen is it to be tangent to y equals x. So you'd want your root to touch like there, if the top of the root is touching exactly there along that line y equals x, then the top of the, well, I guess the bottom of the inverse would be touching right on that line as well. It needs to be tangent. So there's two things you need for tangent. You need same gradient at that spot, and you need to intersect at that spot. Fair enough. But more specifically, that spot is the line y equals x. And so the gradient that we're looking for has to be equal to 1, because the gradient of the line y equals x is equal to 1. We also know that it has to intersect, and that will come into play later. All we're going to be doing is subbing in y equals x for that spot. But anyway, first things first, let's find where f of x is equal to x, right? We know it's going to be, our function f of x has to be equal to the line y equals x. It has to touch. And if you solve that on the CAS, you're going to get plus minus the square root of c minus 1 for x, right? You're going to have your x purely in terms of some variable. Now, the good news is that we know that x has to be positive, since we've seen that if we shift right, that does get us to a spot where there are no solutions. If you were to shift this thing left, very far left, then it would always intersect at some point. Like, for example, if I were to play with the c value and make it more positive on the CAS here, we should see that it gets further and further to the left, and thus these red and blue lines will touch. So if I move this right a bit, you can see it gets further and further away, but it still continues to touch. Right, the blue line is our f of x. We can see it doesn't matter how far I shift this that way, they will always touch. It's only when I shift it left, do they stop touching. Okay, so shifting right is the goal, which means we're going to have a positive x at that spot. Cool. That's why we're taking the positive of that root. All we do from here is try to meet the second criteria. So we want the derivative to be equal to 1 at that spot. And we're trying to figure out what c value will achieve that. So a nice shorthand way of doing it on the CAS is just like this. We say derivative of our function has to be equal to 1. We're solving for c, and we want to have the conditional that x is equal to root c minus 1. Right? Now you can go through and sub in x equals, like you could do the derivative first, then sub in your x, and so on and so forth. This is just a one-liner way of doing it. That's all that's really being done there. When you do that, you're going to get c equals 1. And sure enough, if you were to sub in c equals 1, you can see that they are tangent. They are barely touching at that spot. If we do that on the CAS, we should see the exact same thing. If we bring it over, c equals 1, you can see they're just brushing up against the side of themselves. So, if c equals 1 is the breakpoint, then it means that all c values less than that will cause no real solutions. So if I were to do, for example, c equals 1.5, oh sorry, it had to be c equals negative, yeah, c equals 0.5, that will be less. So I go, any1, define c equals 0.5, hopefully we'll see it a bit nicely. Yeah, okay, you can see it well enough. It's diverging as soon as it gets less than 1. So that'll be the solution for C, such that we have no real solutions. There is no intersection point. Part B of this is that we only had to have one real solution, exactly one real solution. So what do we do here? Well, we kind of already have at least one possible answer for that, and that is when it's a tangent, right? When it is just brushing up against the side. That's going to be c equals 1. That's one possibility. But it's not the only possibility, because we saw that if we were shifting our graph left, then that would also have one real solution. So if I grab the slider again, if I shift it all the way left, you'll see, oh, hang on. Sorry, shift it right, that's a positive c values. If I shift it all the way right, you can see that these are one solution as well. Only one real solution. So now we've got to figure out, okay, how far left do I have to go before we stop having two real solutions? Because if you see here, like for example, c equals 1.5 on the screen share, you'll notice that there's a certain bit of grey area where there will be two real solutions. If you have c equals 1, you're tangent. If you have c equals 1.5, you're in this middle bit here where there's two real solutions for your inverses. And that's because what you want to have happen is you want to have the green starting point above the line y equals x. Otherwise, it's going to come back in on itself and it's going to intersect twice. As long as this green goes above the line y equals x, that starting point, then you'll only ever touch once when this starts to taper off. So, okay, how do we find that? Well, let's just try to make sure that that's the case, right? We want to figure out at what point is it going to eventually go above that line y equals x. Now, the good news is y does equal x. And so if you know that your vertical translation is -1, you would also want your horizontal translation to be -1, since the line y equals x does have the same x and y. And so all you're going to do is pick C such that you have a horizontal translation of -1. And in this case, that'll mean C equals 2. Just a reminder that when you have a coefficient on your x, that does hide what the actual horizontal translation looks like. But okay, so if you chose C equals 2, you would get this. And we did kind of see that at the beginning, right? We saw that as C equals 2, it would touch like exactly there and exactly over here as well. From here, we know that if C gets any larger than 2, it's going to get further away. Like if we see back on the CAS, we go down to C equals 2.5, we can see that it just touches at one point over here on the positive side of the x-axis. And so there you have it. You're going to have your C greater than 2. Doesn't matter how big C gets at that point, they will always touch. And then there was that one option for C equals 1, where it's tangent at that spot. So that's pretty much all there is to that. In summary, you find your x values for where either the inverse or the original graph is tangent to the line y equals x. And sometimes you'll have better luck with the inverse function, sometimes you'll have better luck with the original function, depending on how complicated it is. Like this exam question here, like you can see how complicated that is. You've got a logarithm and a square root and all sorts of nonsense in there. That might not be the one that you want to use. You might want to use whatever h of x was. That'll all just depend on the situation that you have. That's why I say you can use either, because it doesn't matter which way you look at it. From there, if you want to make it tangent, there's two criteria. You need to have your gradients being the same at that spot, and you need to have the intercept being the same at that spot. Which means you're solving for where the function is equal to x, because it's along the line y equals x, and you're solving for where gradient is 1, because the line y equals x has a gradient of 1. You're just going to use a solution from part A as your conditional for part B. And then once you find that breakpoint, you just got to sort of either play with it on the CAS or just observe in your mind what it would take to break that. Like, do I go left? Do I go right? Because in some cases, like in the first example, we had to go right, so we wouldn't touch anymore. If we went right, it wouldn't touch anymore. But if you're looking for the one solution example, we knew we had to go left. We had to go further this way. And even on the CAS here, you can see further left was the goal. Okay, that's about it for that type of function, or that type of question, rather. It applies to all of these kinds of questions. You might have to do things in different orders, depending on how complicated it is, but those are the key things you need to hit for that question.